Welcome to the webinar for February 2025. This month, we're going to be talking about understanding algorithms in the 802.11 standard to become a better Wi-Fi tech. My name is Tom Carpenter. I'm the director of CWNP, and the topic for this month is not so much on understanding every single algorithm in the 802.11 standard, but it is on a method that you can use in the learning process to understand the algorithms in the standard, to document them in a way that you can understand, comprehend, and even regurgitate the actual process flow of the algorithm, which means that you understand it. And here's the big thing. Many times, particularly when preparing for certification exams and things like that, we often have a tendency to do what many of us learned in school, which is this rote memorization process. And that would simply be that we memorize a bunch of facts, right? And here's the thing. When you understand how something works, not just facts about it, then you have the ability to go through that process to find answers, the facts, to various different things and various different questions. And so it's very useful to understand how it works. Additionally, when it comes to analysis and troubleshooting of wireless LANs, it is nearly impossible to do it if you don't understand the algorithms. Now, there's not necessarily a single place in the standard where every single algorithm is just listed in an algorithmic form. They're often included in many paragraphs of text that you read through and then extrapolate out of it a more algorithmic structure. So we're going to talk about that algorithmic structure today. And we're just going to use a couple of examples to illustrate this as a tool and how you might use it to improve your learning and understanding process. We're going to begin by answering the question, how do I secure my connection? So let's assume we're the device, and as the device, we're asking, how do I secure my connection? And specifically, we want to ask, how do I generate the PSK for WPA2 PSK, WPA PSK? How would I generate the PSK if I have a passphrase? So how do we go from passphrase to PSK, from which a PMK can be derived? So let's look at that algorithm and see how it works. So the first thing is that we're going to utilize what is sometimes called a pseudo-code structure. Now, there is no definitive standard for pseudocode that everyone utilizes. I say that, and I'm sure that some who are maybe more advanced in their programming knowledge out there will say, oh, well, there's this and there's that. That's exactly the point. There's this and there's that. There's really no standard for it. So I don't want you to worry using this as a learning tool about complying with some specific standard. What I would suggest that you do is that you come up with a consistent way that you write your pseudocode. So when you're dealing with a decision, how are you going to structure that? Like an if statement, for example. When you need to loop, how are you going to structure that? So the point is, in your algorithm, for the different types of structures you would need to use for that algorithm to work, you want to make sure that you do it consistently, because it's going to help you remember these different algorithms and therefore how these different things actually work. So one good method that you could utilize is you could write your algorithms using if blocks, while blocks, do loop blocks. I know in programming, the do loop is the most avoided structure out there, but in pseudocode, it works just fine because we're not actually compiling this, right? But if you do write your pseudocode in a method that utilizes if statements, that utilizes looping constructs, that sets variables and things like that, then what you'll find is that you can actually pass your pseudocode as is into many large language models today and ask it to write Python code or C code that does what your algorithm specifies. And it can actually write the code because your pseudocode becomes a skeleton for the code that the LLM needs to write for you. So a pretty cool concept if you do use some consistency and common type of structures in your pseudocode. So we have a case for WPA2 PSK, and the first thing we have to do is set the passphrase and the SSID, because as we'll see, these are used in the formula to derive the PSK from the passphrase. We also need to then indicate that our passphrase, from the perspective of the formula that's used in the standard, is actually the passphrase plus the SSID, and not just the passphrase alone. So we'll set the password to equal that. Then we'll set iterations to 4096 because the standard specifies that we must do 4096 iterations. Iterations of what? Our algorithm will tell us. So what we're going to do next is we're going to say while iterations is greater than 0. So as long as iterations is still up there above 0, anywhere between 1 and 4096, we're going to do some kind of a looping structure here. We're going to say new underscore password equals hmax SHA-1 256 of the password. So we're taking that password, which remember was my secure password, my SSID, the combination of passphrase and SSID. We're going to take that and we're going to hash it using the hmax SHA-1 algorithm. And we're going to have that output for us a 256-bit value and store that in new password. Then what we're going to do is just set password equal to new password, and we're going to decrement our iterations variable. So what was 4096 is now 4095. And what this will do is ensure that we go through the number of iterations that are required in order to comply with the IEEE recommendation. And what will happen then is after we hash the hash of the hash of the hash 4096 times, we'll end up with the password variable containing that last one. And then we simply say the PSK equals password. And it looks like we do have a variable typo here. It should be PASSWORD equals new password and not PASSWRD. But that's okay. You understand the point. So this is our pseudocode. Well, where do I get the formula from I kept talking about? Well, that's right out of the standard. So the standard specifies the formula to convert from the passphrase to the PSK. And it says what we're going to do is we're going to use the password-based key derivation function, version 2, PBKDF2. This is actually a function that is defined in an RFC with the IETF. So RFC 2898 defines PBKDF2. So if you want to know all the details about how that works, you can look there. We're not going there today. See, here's our point. Our point is to understand how this process works in 802.11, not to understand PBKDF2 itself. However, if you did want to understand it, then you could go and look at the RFC and look at the process that's utilized there. That would reveal to you that actual function. What we're doing is we're having our algorithm simply use or embed another algorithm, which happens to be the PBKDF2 algorithm. So the passphrase and SSID are combined, and they act as the salt, it's called in hashing algorithms. They act as the salt for the function. And they're hashed 4096 times, and they generate a 32-byte key. Now, 256 divided by 8, 8 being an octet or a byte, is 32. That's where the 32 bytes comes from. And so the end result is that this formula is put into our algorithm because we have to loop over it 4096 times. The variables are simply passphrase and SSID. And our passphrase is my secure password, not very secure, and my SSID is, well, my SSID. Now, here's a big thing to take away from this. When you're defining the algorithms in the 802.11 standard, always ask, what formulas does this algorithm use? And you can substitute synonymously process for algorithm if you want to in this case. Okay, they're not exactly synonymous, but if you're talking about a process in the 802.11 standard, how a process works, there's an algorithm to that. And so you can define the algorithm that the process uses, okay? So when you're going through one of those algorithms or processes, always ask what variables are involved and what formulas are used. When you do that, what'll happen is you'll get more clarity about how this works. So we now know that our passphrase is not our passphrase. Our passphrase is actually our passphrase and our SSID. They're both utilized in this process. We also know that we don't just do one process of conversion, but we actually do 4,096 iterations of conversion. We hash it nearly 4,100 times. And that final hash is what we use for our PSK, and then we derive our PMK from that PSK. Okay, so this is the first example of how you can use an algorithm. And again, I've given you the algorithm here with a little typo in past WRD. I've given you the algorithm here, but what I want you to understand is you want to go through the process of creating this algorithm. And you'll see that they can get a bit more complicated as we go on. Now let's move on to the next one. In this example, we're going to answer the question, how do I transmit data? Now, there are really two primary algorithms in the 802.11 standard for transmitting data. There's the DCF algorithm, and then there's the EDCA. Now, we're going to look at DCF and then maybe surprise you a little bit with EDCA as we talk a bit about it. So first of all, case is data frame to transmit while using DCF. First of all, we need to set a random backoff timer to a random value. We're not going to look at the specific variables for doing that, but we are going to pull that from the contention window values. And then what we're going to do is do a loop. So we're going to say, if not nav equals 0, then we need to decrement the nav. Else, that is the nav is equal to 0. If not diffs wait complete, pause for diffs duration. Else, if the medium is idle, if the random backoff equals 0, transmit the frame. Else, decrement the random backoff. Else, now this is the else to if the medium is idle. So if the medium is idle, we're going to either transmit the frame or decrement the random backoff. If the medium is not idle, we're going to attempt to receive the frame. If the frame is received, we're going to set the nav equal to the duration ID value. And we're going to set the diffs wait complete to equal false. And then we're going to loop. Now let's think about this algorithm. So what we're doing first is we're checking to see if the network allocation vector is equal to 0. So this is what you set when you actually read the duration ID field value from a frame. You set this nav timer, right? And the nav timer needs to count down to 0 before you can really do anything else. This is called virtual carrier sense. So the first thing we're doing is just making sure that we've taken care of virtual carrier sense. There's no use in doing anything else if our nav timer is above 0. And notice that our nav timer comes in down here when the medium was not idle as we're looping through this process. When the medium was not idle, we attempt to receive a frame. If we receive it and we can read it, then we can set the duration ID value and the nav value to the same so that now our nav is set. So if we start at the beginning and nav is not 0, then we're going to decrement the nav. We're going to reduce it, and otherwise we do all the rest of this. Since it was not equal to 0, we've reduced it and we've looped back around, haven't we? So all we do is keep reducing that nav until it's 0. Once it is 0, then we go to the else. Then we say, well, have we waited a diffs? We got to wait a diffs. We got to wait a DCF interframe space. So if we have not waited for that, then we pause. Okay? And then else, we say if the medium is idle, then we got to check our random backoff. So even if the medium is idle, we still can't talk. We got to check our random backoff. If our random backoff is 0, we can transmit the frame. Otherwise, we have to decrement the random backoff. So notice how as we keep going into the nested if statements here, we're actually taking care of the logic of the DCF algorithm that you may have studied already in your CWNA studies. We're accommodating for the nav. We're accommodating for the interframe space. We're accommodating for carrier sense, as well as, of course, virtual carrier sense because of the nav. We're accommodating for the random backoff. All of that is there. And so this is the DCF algorithm. Now let's see the EDCA algorithm. This might surprise you. Wait, it looks exactly the same, except we've changed diffs to AIFS. Well, that's because it is once a frame has been chosen for transmission. So once a frame has been chosen for transmission from one of the EDCA queues, then the algorithm is the same, except we're using an arbitration interframe space instead of a DCF interframe space. And as far as getting our random backoff value, we still set the random backoff value, the random backoff to a random value. We still do that, just like we do with DCF. It's just that the range that we pull from varies depending on the queue that the frame was pulled from. But the actual algorithm, once a frame is selected, this do loop, everything inside of there is the same, except we're using an arbitration interframe space. That can help a lot because a lot of people are overwhelmed when they begin to look at all the details of the EDCA algorithm and the EDCA functions for the queues and all the details about, background and best effort and voice and video and CWMin and CWMax. And then you've got your arbitration interframe space, which is calculated based on other values. And they start getting into all that and they feel like it's hard. But remember, all you're doing is adding more to what you already know about DCF. And when you understand that really all that's changing is there's an outer algorithm, if you will, an outer loop around this loop that is deciding which queue we're going to process a frame from based on the backoff timers for the frames in the queues. And so once you have picked a queue because it had the lowest backoff timer when you grabbed a frame from a queue, then you're just looping through this process just like you do with DCF using an arbitration interframe space instead of a DCF interframe space. So hopefully that helps with that a bit too. Now remember, we want to look at the algorithm, the formula, and the variables. So if we just stick with the DCF interframe space formula, then diffs is equal to a sifs time plus 2 times a slot time. Now you might say, what is a sifs time? Well, a sifs time is the short interframe space time, okay? And the slot time is the duration of a slot for a given physical layer. Now, the reason these are not listed as absolute times here is because they differ for different PHYs. So for example, these variables for 802.11n and 2.4 gigahertz, a sifs time is 10 microseconds. A slot time is either 9 or 20, depending on whether you're using the short or long slot time. The reality is if you have 11G or B or 11 prime devices in 2.4 gigahertz, then you may be using one of these slot times over the other, right? So you've got to have backward compatibility. So those are your variables. And then for 5 gigahertz, it's just a sifs time is 16 microseconds and a slot time is 9 microseconds for 802.11n. Now, again, this can change for 802.11a or 802.11ac or AX or BE or whatever. So the different PHYs can change these variables. But remember, they're still the variables. There's a variable called a sifs time. There's a variable called a slot time. Okay? They're still the variables. Those variables are still used in the formula. And so that is how we calculate the interframe space. Now, we could also look at the variables for how we calculate a random backoff timer, as I've already mentioned, CWMin and CWMax, and how those are utilized to do the random backoff timer. And again, because I'm talking to you about this as a learning tool, I would indeed encourage you to investigate those other formulas and variables so that you can plug them into the algorithm that we have talked about. Next, we want to talk about one final example of this. How long should I wait to retry? Now, for this example, I'm going to take you a step further and actually show you some of what the standard actually says about this. So within the standard, we actually have a section in clause 10, where it says, after transmitting an MPDU that requires an ACK or block ACK frame as a response, the station shall wait for an ACK timeout interval with a value of A sifs time plus A slot time plus ARX phi start delay starting at the phi TX end confirm primitive. If a phi RX start dot indication primitive does not occur during the ACK timeout interval, the station concludes that the transmission of the MPDU has failed, and this station shall invoke its backoff procedure upon expiration of the ACK timeout interval. If a phi RX start indication primitive does not occur during the ACK timeout interval, the station shall wait for the corresponding phi RX end indication primitive to determine whether the MPDU transmission was successful. If the station recognizes a valid ACK frame addressed to the station and corresponding to this phi RX end indication primitive, this recognition shall be interpreted as successful acknowledgement. Okay, so let's talk about the algorithm that's in here. Okay, there's an algorithm here. And basically, the algorithm is saying that when you transmit a frame, then starting at the end of that transmission, that's phi TX end confirmed. So the phi has sent a communication up to the MAC saying, I confirm, I sent it. If a phi RX start indication does not occur during the ACK timeout interval, well, what's that interval? It's A sifs time plus A slot time plus ARX phi start delay. That is our formula. We'll see that in a moment. We're going to wait that amount of time, and while we're waiting, we're listening to see if the phi says to the MAC, hey, I've got a frame coming in. And if it does say, hey, there's a frame coming in, we're going to process it and see if it's our acknowledgement. If it's not our acknowledgement and no acknowledgement came in during that ACK timeout interval, then we'll do a retry. So to answer the question that people often ask, because we always say, well, if you send a frame and you don't get an ACK, you retry sending the frame. How long do you wait? Do you wait an hour? Do you wait a week? How long do you wait before you retry? The 802.11 standard gives us the answer. And notice the creative way the standard does all of this. So we're using that A sifs time and A slot time and ARX phi start delay variable. So we're using variables that can vary. That's why they're called variables with the different phis. And yet this paragraph will be true regardless of the phi. That's the beauty of it, okay? So this is our formula and our algorithm. But again, as I said, the algorithm isn't so much listed in steps here. It's just a couple of paragraphs of text. There's actually another paragraph on the following page that also applies, but it doesn't extend this part of the algorithm. It talks about something else. So what is our actual algorithm then? That's the question. Well, let's take a look. Basically, we're going to say case transmitted frame requiring ACK. So we've sent the frame. While the wait time is less than wait time formula, listen for frame. If ACK frame received, process the ACK. Set the wait time equal to 0, exit. Else, increment the wait time. If the wait time is greater than or equal to wait time formula, increment the retry counter. Retransmit frame. So do you catch what our algorithm is doing? It's saying, look, go ahead and transmit the frame. When you're done transmitting it, during the wait time, check to see if there's an ACK frame. If one ever comes in, go ahead and process it. Set that wait time to 0 and exit. And then we say, if the wait time is greater than or equal to the wait time formula, increment the retry counter and retransmit the frame. Because our wait time ends up being the entire delay period. Based on the formula, remember, A sifs time plus A slot time plus ARX phi start delay. And again, our variables, so it's different with 802.11 and 2.4 gigahertz than it is with 802.11n in 5 gigahertz, right? So notice we've got 10 microseconds, 9 or 20 microseconds, and 28 or 24 microseconds. In 5 gigahertz, we've got 16 microseconds, 9 microseconds, and 28 or 24 microseconds for 11N in these two different bands. And so those would get plugged into the formula. And by the way, just so you know, again, we'll look here in the standard, these tables exist for the different physical layers where appropriate. Now, some of the physical layers simply use the values of other physical layers, and they simply tell you that they implement the phi characteristics from the other physical layers rather than having a new table. There's no need for a new table if we're just using the same values. So some of the newer phis will simply refer back to the older phis and say, we're using that older phis technology. And so right here, you can see the A slot time. And notice the difference between 20 microseconds versus 9 microseconds is based on whether .11 operating classes required is false. Well, .11 operating classes required has to do with the backward compatibility capabilities. And this can be set in the beacon frames of the APs, and it can also be inferred. So just based on what's going on the channel, it can be inferred by devices, and they can set this .11 operating classes required parameter accordingly. So there are various ways within the standard that can be set. And then once those are set, it's going to determine whether you're using the long slot time or the short slot time. Now, the ASIFS time is simply 10 microseconds in 2.4 and 16 in 5 gigahertz. And you can see the ARX phi start delay is 28 microseconds if you're in mixed mode. And if you're in HT Greenfield, 802.11n only, then it's 24 microseconds. So you don't see that as much. It's usually the 28 microsecond ARX phi start delay. So there you have it. Those are 3 examples of algorithms, formulas, variables. Now, before I summarize, let me show you what I was talking about a bit earlier. I'm going to bring in here exactly what I said. So what I've done here is I have taken my pseudocode right here, which it's not wanting to display for some reason. But this is the pseudocode that I had in the slide for DCF. And what I did is I gave it a directive. I said, this pseudocode defines the algorithm for communication using DCF and 802.11. Can you write a simulation in Python that will implement this algorithm and allow me to run it with different numbers of clients accessing the same AP based on this algorithm so we can see how long the average client would have to wait before it could transmit a frame as more clients are added? The script should start by asking me how many clients, what percentage of time they desire to transmit, how large the average transmitted frame is, and the average data rate of the devices. Using these inputs, the script should simulate the algorithm and report on how long the average client will have to wait every time it has a frame to transmit. And then it said, sure, I can do that for you. And it creates this. Now, I'm not going to go through every detail of this, but you can see that it's going through, it looks like 100,000 slots. And it actually was intelligent enough, by the way, I didn't tell it this, it was intelligent enough to know, okay, I'm going to do this based on slot times so it's more realistic instead of just based on a certain number of seconds. So in the end, it runs for varying numbers of seconds depending on how many client devices that I need to use, because it's trying to accommodate my number of slots that I need to transmit devices. So then it's going to address clients, and you can see up here it's defining our simulation variables for the clients. And then what we're doing is we're randomizing our clients and transmit probability and various things like nav timers and all of that. Look at this, we're checking to see if the medium's idle or not, and then doing different things depending on whether the medium's idle. So it's actually taking in the information that I gave to it in the pseudocode, and it's also utilizing its knowledge of the 802.11 standard. That's where it gets slot times and things like that. So it's actually pulled in some extra things along the way. Now, would it be perfect the first time? Maybe, maybe not. You'd have to look at the code to see. This simulation is actually pretty good. It's not too bad. And I have actually downloaded it and run it a few times for you to see here. So here I ran it with one client, 20%. So each of those one clients wants to transmit 20% of the time. The frame size on average is 1,024,000 bits. And the average data rate in bits per second, I just put it at 54 million. So the average wait time is 0 microseconds. We sent 48 transmissions. So it's 0 microseconds because I'm the only device, right? So I don't really have to wait is what it's telling me. Then the doubling it to 2 clients, all the other parameters the same. Now the average wait time is almost 2,000 microseconds. Then adding it to even larger numbers of clients, we've got 10 now. Now we're averaging 14,252 microseconds. And when we have 100 clients, we're up to 40,540 microseconds. Now, by the way, that's still, in reality, I mean, you're still going to transmit 6 or 7 times a second. And so, that might seem like you don't have much transmission opportunity, but you do. Now, we could run this one last time, really taking it up and straining it. So we can say, hey, what if we have 250 clients and they all want to transmit 50% of the time, and they're transmitting those 1 million bit size frames, and we're doing 54 million bits per second. It's going to take a little longer to run than what it might otherwise because we now have to simulate 250 clients. And as you can see, there's a pause here. Why is that? Because this is not just simulating an attempt to transmit a frame. It's simulating multiple attempts to transmit a frame while having to wait on other clients to transmit their frames. And since of these 250 clients, 50% of the time, each one of them wants to talk, we're going to get a more significant delay now in being able to transmit our data. So let's see what the result is when it gives us the final from this particular submission process. All right, I went ahead and sped forward to the end of that for you, and you can see that this time, to do our 48 successful transmissions, we had a delay each time, a wait time each time of 111,531 microseconds, so more than double what we had when we only had 100 clients. And so this is why you'll hear me often say when I teach CWNA or I teach CWDP, I say, look, just because an AP can support 1,000 clients, it doesn't mean you want 1,000 clients connected to that AP, because the wait time is going to get larger and larger the more clients you have. Now, granted, you're not going to see a 50% desire to communicate for each client on average in most of those kinds of networks, but you still get the point. The more devices you have, the more wait time you have, because it is a shared medium. Now we can optimize that instead of this DCF algorithm using an EDCA algorithm, right? Where we give priority to voice and video. And that can help with those types of streaming applications, but that doesn't help my email checking. My email checking is going to be slower because it has a lower priority. So I'm actually slowing that down because I've got so many devices on the AP. I'm slowing down the email checking, the web browsing, the other things that people do in order to accommodate those high priority streams. So you've got to keep all of that in mind and think about then what is the load that I want on my APs. And why can we do all of that? Because we understand the algorithm. We understand the formulas, we understand the variables, and we can put it all together. Now let's just look at one other example here. I also did the example for our pseudocode. This time it's going to show me my pseudocode. So this is the pseudocode we saw, even with the little typo. And even with that typo in there, it still understood it with pass WRD instead of word. It still understood what I did, and it created the script for me. We're not going to run this script like we did the last one, but you can see I simply said the attached is a sort of pseudocode for generating the PMK from a PSK based on the 802.11 formula. PBKDF2, passphrase, SSID 4096, 256 divided by 8. Please write Python code to implement this. And then what it did is it took advantage of the hash lib, a library that comes with Python, and it created a function called password-based key derivation function 2 underscore HMAC underscore SHA-1, passing to it password, salt, iterations, and the key length. And then you've got your arguments and some description of what the function does here. And then we're checking our key length, and then we're deriving our key. And here's an interesting thing. Notice the iterations. So we've got our iterations variable right there, which is set to 4096. So we've got our iterations variable. And we're saying if iterations is greater than 1 for j in range, iterations minus 1. So the range function in Python is inclusive, so it starts at 0. Therefore, we don't want to go from 0 to 4096. That would be 4097 iterations. We want to go from 0 to 4095 to get 4096 iterations, hence range iterations -1. And then all we're doing is we're saying 4096 times set the variable u to equal hmac SHA-1 password u. And what that's doing is it's filling u with the new value, but passing the current value of u into the hmac SHA-1 function. So again, we're not reinventing the wheel. There's already an hmac SHA-1 built into HashLib, so it's simply utilizing that. And then in the end, it's going to return that key, and we can see right here, it's printing out the hex version. We're doing the hex method with the PMK object, so we're printing out the hex version of our pairwise master key by doing that. And you can see that it gives an explanation for how it's done and so forth. Now, one of the things that you can do is in the 802.11 standard, in the appendices, there is an example of implementing this. It doesn't give you code. It simply says, if this is your passphrase and this is your SSID, then this should be your key. So it gives you that. So you can actually plug into this the examples that it has in the standard and see if your Python script generates the same key as the standard says should be generated. If it does, you know then that this Python script implements it appropriately. Pretty cool. So what we've learned then is that an excellent method to learn how these processes work in 802.11 is to create your own pseudocode of algorithms. Or in other words, create your own algorithm. And remember, an algorithm is just a sequence of steps that gets a job done, that usually takes inputs and generates outputs. And so create your own pseudocode for your algorithm, know the formulas that you need in that algorithm, and the variables the formulas are going to use. And when you understand those three components, algorithm, formulas, variables, then you understand how that process works. And now you've truly learned that process. And that means that not only are you well prepared for an exam, but you're prepared to troubleshoot, to analyze, to design, to work with these technologies. So in summary and in closing, remember, know the algorithms, know the formulas, know the variables, know how it works. Thanks for viewing this month's webinar.